So now we can define the Hessian of a scalar field. So the Hessian of a scalar field is a matrix that organizes all of the second order partial derivatives of the function. So the notation we'll use here is HF, and if our scalar field is on n variables, the Hessian is an n by n matrix where the ij entry is the second order partial derivative with respect to xi and then xj. So the 1, 1 entry is f sub x1, x1. The 1, 2 entry is f sub x1, x2. The 1, n entry is f sub x1, xn. The 2, 1 entry is f sub x2, x1. The 2, 2 entry is f sub x2, x2, so on and so forth. Now, there's something kind of cool about this situation, because here we're studying an n by n matrix filled with second order partials. But Clairaut's theorem tells us that some of these partial derivatives are related to one another. Remember, f sub xi xj is f sub xj xi. It doesn't matter which order we take our partial derivatives in. In particular, what that means is that if we look at the entries off of the diagonal here, they should be paired with the entries across the diagonal. So f sub x1, x2, that's the same as f sub x2, x1. F sub x1, xn, that's the same as f sub xn, x1. F sub x2, xn, that's the same as f sub xn, x2, so on and so forth. Well, if all of these entries across the diagonal are paired with one another, what does that tell us? That tells us that this Hessian matrix is a real symmetric matrix. So that's by Clairaut's theorem. Clairaut's theorem tells us that the Hessian derivative of a scalar field is an n by n real symmetric matrix, and we know a lot about real symmetric matrices. So let's look at an example here. In this situation, I'm studying a scalar field on 3 variables. This is f of xyz equals x squared z plus y cubed over z. I could calculate the Jacobian derivative of this scalar field. So this is a function from R3 to R1. So the Jacobian derivative should be a 1 by 3 matrix. And the 3 entries in this matrix should be the derivatives with respect to x, with respect to y, and with respect to z here. So I have f sub x, f sub y, and f sub z here. Now I can construct the Hessian matrix. This will be a 3 by 3 real symmetric matrix organizing all of the second order partials. So the 1, 1 entry, that's f sub xx. That's the derivative of f sub x with respect to x, which here should be 2z. The next diagonal entry is f sub yy. That should be the derivative of f sub y with respect to y. And if we're looking at f sub y, that's 3y squared over z. That should be what? 6y over z. And if I look at the third diagonal entry, that's f sub zz. That's the partial derivative of x squared minus y cubed over z squared with respect to z. If I take that partial derivative with respect to z, I should end up with 2 times y cubed over z cubed. So this first term goes to 0, and the second term is really negative y cubed times z to the negative 2, and when I differentiate, I get 2 y cubed over z cubed. So that's the diagonal entries, which are the second order non-mixed partials. Now let's move to the mixed partials, which should occur in pairs by Clairaut's theorem. So what is f sub xy? That's the same as f sub yx. Well, I could go to f sub x and take a derivative with respect to y. F sub x here is 2xz. When I take a derivative with respect to y, this should give me 0. What about f sub xz, which is the same as f sub zx? I can go to f sub x and take a derivative with respect to z. That should give me 2x here. And then finally, for my last 2 second order partials, this is f sub yz, which is the same as f sub zy. I can go to f sub y here and take a derivative with respect to z. In this case, I'm differentiating 3y squared over z with respect to z. This should end up giving me negative 3 times y squared over z squared. So I've successfully constructed my Hessian derivative here, which is, as promised, a 3 by 3 real symmetric matrix.